Hello students, today we will discuss about instruction level parallelism. So we have already mentioned or discussed about pipelining, what are the advantages of pipelining and where we are using pipelining, what is the purpose of using pipelining, etc. So instruction level parallelism is also a concept that is related to the implementation of pipelining. So the overlap among the instructions that is part of a pipeline is actually called as instruction level parallelism. So as the name indicates, instruction level parallelism indicates different instructions are executed in parallel at the same time by using different stages. So it is actually used for improving the performance of the entire computer system. So there are two approaches that are used for exploiting parallelism. First one is related to the hardware. That means we are actually trying to implement the parallelism dynamically with the help of hardware. And the second approach is by using the software technology, which is usually done statically at the time of compilation. So there are two basic methods that can be utilized for implementing instruction level parallelism. The simplest method or the common way to increase instruction level parallelism is by exploiting parallelism in the case of iterations of a loop. So normally if we are having a loop with 100 iterations or 1000 iterations, we need to perform the same task multiple times. That means we need to execute the same thing n number of times according to the loop. So that means it is actually a larger task that actually takes more time to execute. So if you try to parallelize or execute the loop in parallel format, so that the entire execution of the loop can be done in less amount of time. So this type of parallelism is usually called as loop level parallelism. Now the basic compiler techniques for exposing instruction level parallelism. So initially we are considering about the usage of instruction level parallelism by using the second method that is called as the compiler technique. That means software technology we are using for implementing the instruction level parallelism. So the aim of compiler techniques for exposing instruction level parallelism is to use the basic compiler technology to enhance a processor's ability to increase the instruction level parallelism. And these techniques are usually crucial for the processors that uses the static issue or static scheduling. That means the whatever steps that is to be executed are statically given. So all the statements that is to be executed, what are the statements to be executed, the order of execution, everything is given statically itself. So if the order is clear, we can have some enhancement added to the compiler so that we can increase the parallelism of the set of instructions that are given to the system. Now basic pipeline scheduling and loop unrolling. So for the compiler based technology for implementing instruction level parallelism, we are using static pipeline scheduling. That means we need to make the plan or schedule for the execution of various instructions, and second stage we need to do an additional operation that is called as loop unrolling. By using loop unrolling, we can even do parallelism on the set of iterations, the number of iterations that are present in a particular loop. So to keep a pipeline full, parallelism among instructions must be exploited by finding sequence of unrelated instructions. So it is always better to find the unrelated instruction, so that normally if one instruction is depending on another instruction, it is very difficult to implement parallelism. So it is always better to execute unrelated instructions, so that one will not be affecting the another instruction. So from the set of instructions available, we need to find out the set of unrelated instructions, and if we implement this parallelism on these unrelated instructions, that can be executed independently, and if we implement that parallelism on these instructions, we can actually save the total time taken for the completion of the entire execution. And the different instructions that are unrelated, and if they are overlapped, with the help of pipeline, we can exploit more parallelism on that particular set of instructions. So normally there will be the occurrence of pipeline stalls when we do execute different number of instructions simultaneously. That happens only when we are having some dependent instruction that is available within the set of instructions. So normally if we are having dependent instructions available, we can have some stall, some delays in between the execution of instructions. So as we are trying to execute unrelated instructions, similarly we need to try to find out the dependent instruction, and these instructions must be separated from the source instructions, so that it will not affect one another. So it is to be separated by keeping a distance in the number of clock cycles. So if some dependent instruction to be executed next, that instruction to be delayed for some more clock cycles, so that some other instruction can be utilized before the starting of this dependent instruction, because dependent instruction always expect the result of the previous instruction. Usually if it is directly entered into the pipeline, they actually not get the corresponding result required for this particular instruction. So just make some delay, so that when this dependent instruction start execution, it will actually receive the result of the previous instruction. So first point is we need to find the unrelated instructions. Second point is to make a delay on the dependent instruction that depends on the result of the previous instruction. So when we implement this instruction level parallelism by using compiler technique, we need to assume that the functional units present are fully pipelined or replicated. That means the functional units are further divided into sub units, and that can be pipelined, or we should have multiple number of functional units available within our system, so that an operation of any type can be issued at any time in every clock cycle, and there are another assumption that there is no structural hazards present in the entire set of the entire system, because we assume that we have multiple functional units available, as well as the functional units are replicated. So we are doing all these assumptions on the implementation of compiler technology that is used for implementing instruction level parallelism. Now for giving more explanation on pipeline scheduling and loop unrolling, we will first look into the simple code, and by using this code we will try to explain how the instruction level parallelism can be solved by using compiler technique. By using a compiler, how we can solve the problem or how we can increase the speed of execution of a particular loop. So just look at the following code, which consists of a single for loop. For I equal to 1000, I greater than 0, I minus, and within the loop we are having a single statement, x of I is equal to x of I plus s. So h of I is the current array location. Initially it will be 1000. H of 1000 is equal to h of 1000. So initially whatever value is there in the 1000 location will be added with a scalar value s. A constant will be added to the same array content, that is 1000 array location, and that value will be assigned to the 1000 array location. So that is happening with the first iteration. Now second iteration, I is equal to 999. Again what will happen? H of 999 is equal to h of 999 plus a scalar value. So it will affect some other array location, h of 999. Similarly, if we move to the next iteration, what will happen? It will work on 998. So h of 998 is equal to h of 998 plus the scalar value. So 1000 times the loop will be repeated. Now we can see in this particular example that each time when the loop is being executed, different memory locations are being affected. That means all the instructions present in this particular loop statement are independent. For each iteration they are having independent statements that is to be modified. So one array index to be modified, it will not depend on some other memory location. So we are having 1000 different statements. So each iteration we are having one statement. So totally we will be having 1000 statements, and all these 1000 statements are different. So this loop is to be executed 1000 times. These 1000 statements are to be executed, and these 1000 statements are independent. Now let us see how this will be implemented by using the mechanism of pipeline scheduling and loop unrolling. So we are actually trying to apply some compiler technique for exploiting instruction level parallelism. For that we are using pipeline scheduling and loop unrolling. So we can see that in the previous example we can see that the loop is parallel and each iteration is independent, that I have already mentioned. Now we can show how we can use parallelism to improve its performance for a MIPS processor pipeline with the latencies that will be happening in between the execution of various iterations. Now for that activity, the first step is to translate the given for loop into the corresponding assembly language statement. So now we are reusing MIPS processor here, so we will be converting that for loop into MIPS assembly language statements. So before moving into the assembly statements of the corresponding the given loop, we will look into the diagram that is given here, that is actually required for the explanation of the MIPS assembly language implementation of the given for loop. Now in this particular case we actually require two units. One is the integer unit, that is for integer related activities, and second is an FP adder that is used for floating point addition purpose. So in this loop we actually require integer unit for store and load operation, because for calculating effective address we require the integer unit. So only for that purpose this uses an integer unit. So you might be remembering in the previous session we discussed about multi-cycle operations, where we are actually giving different number of functional units, or functional units are being pipelined for various activities. If it is for integer, floating point adder, floating point multiplication, integer multiplication, etc., etc. So for this middle part, for the execution, we are actually using different functional units in parallel for different types of operations. So you might be remembering the diagram with instruction fetch, instruction decode, and several levels of functional units with multiple number of functional units. So for this particular given for loop, we require only two units. One is an integer unit and second one is an FP adder. Okay, so this integer unit is used for calculating effective address for load and store operation, and this FP adder is used for adding the array index content with the scalar value. So we are using an floating point adder, and that is having multiple functional units available, or this is actually being pipelined. This unit is actually being pipelined. That means it is divided into number of further other stages for the FP adder execution itself. Now, as I have mentioned, there are different situations that may happen between the different instructions present in our entire iteration. So sometimes we will be requiring the effective address calculation, sometimes we will be requiring the floating point manipulation, sometimes there will be some load, sometimes there will be some store, sometimes there will be floating point operation. Mostly there will be floating point operation happens with this particular iteration, and sometimes we will be having effective address calculation for load or store operation. Okay, so we are simply considering some of the operations here. Now in this table, the first column indicates the instruction producing a result. So we are giving some, we have given some examples where some instruction that is actually producing a result, and the second column indicates the instruction that using this result. So this will be producing a result, and this will be utilizing the result produced by the first instruction. And in the third column we are mentioning the latency that may happen between the result production and the usage of result into the second instruction. So we have selected some of the major instructions that are actually required for the execution of the above given iteration. So there will be some latency between the different set of instructions, that is actually according to the order of instruction that are given for the execution. Now first point is, first instruction that produces the result is a floating point ALU operation. So floating point ALU operation will happen using this particular order, and the second one is another floating point ALU operation. So that will also pass through the same area. So one floating point ALU will produce a result, and that result will be utilized by the second ALU operation. So this is the order of the first ALU operation: instruction fetch, then instruction decode, then it will go through instruction execute, first stage, second stage, third stage, fourth stage, and here it will be actually producing the result. And from here only the second FP ALU operation can receive the result. Okay, so assume that just after the second, so this is the first instruction and this is the second instruction that expects the result of the first instruction. So second instruction in the pipeline stage, it will start from here. So here we will be having instruction fetch, then here we will be having instruction decode, then it will try to execute, but the problem is it expects the result of the previous instruction. So this stage it will not get the result because result is not yet generated. This stage also it will not receive the result because result is not generated. At this stage also it will not produce the result because after this stage only it is producing the result. So this 3 clock cycle, instruction 2, that is this instruction need to wait, and that is indicate that as the latency between these two set of instructions. Okay, I hope it is clear, because in our previous example when it is being converted into MIPS assembly language format, there will be some floating point ALU operation and a second FP-ALU operation that expects the result of the previous FP-ALU operation. If that happens, automatically we can say that there is a 3 clock cycle delay in between. So we can set that 3 delay as a stall that is being generated between two set of insertion. So that much time we need to have a delay. Now we will look into the second thing. First insertion is FP-ALU operation and second insertion is a store double operation. So first insertion FP-ALU will happen, that is through this way, and a store double will happen with this way. So this store double expects the result of this is the first insertion and this is the second insertion. So first insertion will produce the result at this stage, and this insertion actually expects a result that is to be stored at this particular stage. Okay, so let us see what will happen. So insertion fetch decode EX, 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 EX. Here it will be producing the result. Now in the pipeline the second insertion also arrives. So for the second insertion fetch will be happening here. Then I'll show this path. Insertion decode will be happening here. Then it will go for EH stage, effective address calculation. Effective address will be calculated by using integer unit. Then some value that is being generated by the first insertion to be stored into this memory. So next stage is memory stage, but what is to be stored will not be received at this stage, even at this stage. So that means there we will be having a 2 clock cycle delay. That is actually the latency between one FP-ALU operation and a store operation. So whenever in our set of instruction, if the first instruction is an FP-ALU operation and the second instruction is a store operation, we can automatically set a latency or stall of 2 clock cycles in between. Then look at the next one, third operation, a load double and an FP-ALU operation. So load double will happen through this way. So this is the first instruction, and FP-ALU will happen through this way as the second instruction. So what will happen with load double? Insertion fetch, insertion decode, then execute, then memory. So after the memory stage only the load will be happening. Load will be completed after the memory stage. Okay, now after that this FP-ALU operation begins. It will start from here, insertion fetch, because as it is pipeline it cannot start from this stage. Insertion fetch, insertion decode, then what will happen? Then EX, it actually expects the result of load double, and after that we expect the FP-ALU operation. Okay, so it will actually have a latency of 1 clock cycle if we pass through the same set of instructions one after another. So load will be finished after memory stage. So similarly after that it expects a result from the load. So after the memory stage only. So after 4 stage 1, 2, 3, 4, after 4 stage it will actually expect the result of this memory. So that time there will be the delay of 1 clock cycle here. So normally if there is a load double and an FP ALU operation, there will be a latency of 1 clock cycle. Then next one is a load double and a store double. So both will happen through this way. This is the first instruction, that is load double, and second instruction will also pass through the same way, that is a store double. So what will happen with load instruction fetch instruction decode EX memory? So this stage load will be completed. Then for store instruction fetch instruction decode EX, then memory stage. So just after this stage it expects the store. So just after this clock cycle it will get the value of this load. So automatically there is no delay between these two set of instructions. I hope it is clear. So these are only some sample set of instructions where we can have some latencies happen in between the different set of instructions. So why we have taken these set of instructions? Because these instructions are required for our previous mentioned for loop. Okay, now we will look into the assembly language version of the previous for loop. So this is the assembly language version of the previous for loop. This is the starting of the loop, first load operation. So into this memory location, from this memory the array element will be loaded. It is stored into F0, that is indicating the array element. Then a floating point add will be happening with this array element with F2. F2 is a scalar. So array element will be taken from the address into register F0, and F0 will be added with the scalar. Then the result will be stored into the same address 0. Then what we are doing is we are using a double add using unsigned integer, that is for decrementing the pointer, that is the decrement of from 1000 to 999. So R1 which is the 1000 array location will be decremented. R1 comma we are adding a -8, that is the byte value of that particular integer value. So each time 1 byte will be reduced for decrementing the pointer. So here it is usually 8 bytes, usually referred as double word. This is the decrement operation. This is in terms of MIPS assembly language statement. Then after that we are checking a condition, branch on not equal to R1 comma R2. So this R1 whatever value, so after reducing the 1000 to 999, so we are getting 999 here, that will be compared with R2. R2 is the value. R2 is the value that is pre-computed, that is 8 of R1, that is it will be compared with the last value, that is 0. So 1000 to 0. So here it will be having the value 0. R2 is the last value, R1 is the 1000 value. So that will be compared. If they are equal, if they are not equal, the loop will be continued. This is the way how these instructions are being executed. So here we can see a load operation and an arithmetic addition operation. There is an add and store operation in between. There is a store and double add operation in between. Then there is a double add and a branch operation in between. So different types of instructions are coming one after another. So in our previous table we have seen some of the instructions and the possible latencies in between those set of instructions. So based on those instructions we will see what will happen to this set of instructions in our next slide. Now without any scheduling, normal way, if they are being executed, what will happen? The loop will be executing as follows, which takes 9 clock cycles. So in between load and add, so this is the same set of instructions. So these are clock cycles starting from 1 between a load and add. So just go back to the previous diagram. Between a load and add, between a load and add, we are having a 1 clock cycle delay. So similarly for this load and add, we are having a 1 cycle delay, that is given as a stall. Similarly between an add and store, there are 2 stalls. So that is already given in that table, you can refer to that also. So 2 stall will be generated here, 2 cycles are being wasted. Then we are having a store. Then between store and FQ there is actually no delay. Between an FP and branch operation, which is not mentioned in our previous table, there is actually a single stall that will be generated. Okay, so that is only a sample table given in the previous table. Not all the stalls or all the latencies are not mentioned there. So totally for instructions 1, 2, 3, 4, 5, totally we are having 5 instructions, but it will take 9 clock cycles because 4 stalls are generated because of the dependency, because this is depending on this one, so there will be a delay here. The store is depending on add D, so there is 2 stall. Similarly, there is no dependency, so there is no stall. Here also there is a stall because this branch is depending on this operation. So totally we are having 9 clock cycle that will be taken for the completion of one particular iteration. So totally if you are having 1000 iteration, 1000 into 9, totally 9000 clock cycle will be taken for the completion of the entire for loop. Okay, 9000 clock cycle. So just remember this number, 9000 clock cycle for the completion of the entire loop operation. Now we will try to schedule. Now we can schedule the loop by obtaining only 2 stalls and reduce the time to 7 clock cycles. So what we are actually, so these are the compilation technology that we are trying to implement. Okay, so what we are actually doing here, so first it will do load operation. Then we have seen that there was a stall between load and add, so compiler will automatically take another instruction which will not affect the any other instruction. This double add, that is decrement statement will be added as the second statement. So compiler will automatically move this instruction over here, and there is no stall between these two, and there is no stall between these two. Then we are doing add, then we are doing store operation. So here you can see there is 2 stall between add and store. Then apply the branching condition, branch on not equal to R1 comma R2 loop. We are actually following the same set of instruction, but when it is being modified from this location to this location, the total number of cycles it takes is 3 plus 2 plus 2, that is 7. So 2 stalls, 2 clock cycle we have saved. So totally it is 7 clock cycle for one iteration, and for 1000 iteration it will be 1000 into 7, that is 7000 clock cycle. So previous example it takes 9000 clock cycle to complete the entire loop, but if you are making this change, 2 stalls are being reduced for each iteration. So For the total iteration, totally it will take only 7000 clock cycles. So we are actually saving 2000 clock cycle time for the execution of this entire for loop. So we complete one loop iteration and store back one array element every 7 clock cycle. Okay, now we are having 7 clock cycle, but the actual work of operating on the array element takes just 3. So the actual operation portion are load, add and store, and the other 4 clock cycles. So among these 7, the other 4 clock cycles consist of loop overhead, means 2 loop branching operations and 2 for stall. So the actual operations are only load, add and store, and other 4 clock cycles are because of stall as well as loop overhead, that is the operations related to the loop, that is d, add, unsigned integer and branch on not equal to, and 2 stalls that happens between these operations. So to eliminate these 4 clock cycles, we need to get more operations related to the number of overhead instructions. So how we can eliminate these 4 clock? So we cannot do anything on this load, add and store, but we will try to reduce these 4 clock cycles, which is actually loop overhead. So what we can do, we will see, we are actually using a mechanism that is called as loop unrolling. So initially we are having some set of instructions available. They may be dependent instructions. So initially we are directly taking those instructions. So when it is given to the compiler will do rearrangement in order to reduce the number of clock cycle. And second thing is, again for iteration, we are actually reducing the clock cycle from 9 to 7 per iteration. Now 7 itself is more. So how we can reduce that? We are using, so all this happens because of the scheduling, the pipeline scheduling that is being implemented by the compiler. So even if we want to reduce those number of clock cycles that is totally required for the entire loop operation, we can use the process called as loop unrolling. It is used for increasing the number of instructions relative to the branch and overhead instructions. So when we use loops where we actually require the usage of more branch operations and the overhead because of the creation of the other set of stalls. So what is this unrolling? Unrolling simply replicates the loop body multiple times. So here normally, if I say in a simple term, from 1000 to 0, we are repeating the loop 1000 times. Then each iteration, so if we do 5 operations together, for example 5 operations together in one iteration, and next iteration again 5 operation, if we do in this way, that means here 1000 to 0, each iteration we are doing only one, we are executing only one statement. But now we are going to unroll. We are going to unroll the loop by adding 5 statements in a single iteration. If you do like that, we can reduce the number of iterations. So for example, if you are having 100 iterations and each iteration if you are having 5 statements, so we can reduce the number of branching. So we are actually having branching overhead. So in order to reduce that branching overhead, we are trying to reduce the number of branches itself. So 100 iteration, each iteration we add 5 statements of 5 iteration. So each iteration will be having 5 statements to be executed. So totally we will be having only 20 iterations. 20 into 5, 100. Otherwise we need to have 100 iterations. 100 times branch overhead will happen. But if you reduce that by unrolling the loop by adding 5 iteration statements into a single iteration and make the branch to be executed in only 20 times. that is actually called as loop unrolling. So this loop unrolling can also be used to improve scheduling, so that if we improve the schedule, we can reduce the number of clock cycle also. So first point is, by unrolling we are reducing the branch overhead, and also we can improve the scheduling. So we can reorder the elements in a better way, so that we can reduce the number of stalls also. It allows the instructions from different iterations to be scheduled together, and if you replicate the instructions when we simply replicate the instructions when we unroll the loop, the resulting use of the same registers could prevent us from effectively scheduling the loop. So we will see examples, then only you will understand this. So you will want to use the different registers for each iteration. So when we unroll the operation, unroll the iteration, we need to do 5 different statements. 5 different statements within a single iteration. We need to refer to memory locations by using registers. So that situation we need to use different number of registers. So that is actually an additional requirement. So we are actually adding some enhancement to the architecture itself by adding more registers. So we require more registers, but we are trying to improve the parallelism. So parallelism can be improved, but there is a drawback of having the usage of more number of registers. But we are trying to improve the pipeline. So just look at how we can do loop unroll. So this is the starting of loop. So here we are adding a load operation, add operation, then store. So this is one statement. Then normally in the previous case, after this we are doing DA, DDI and branch on not equal to, but we are not doing that here. So within the same loop I am adding next load, add, store. Here again we are dropping these two statements. Again within the same loop we are adding the load, add and store again. Again the load, add and store again. Then finally we are adding the add unsigned integer and branch on not equal to. Now you can see the difference here. Initially we are loading the 0 location to F0, then that will be added with scalar. The result will be stored in F4, then F4 is again stored back to the same memory location. But second time when we are loading, we need to load the next element. That means minus 8 R1. That means from 1000 to 999. That is stored in a different register F6. So we need to use different set of registers here. Then that will be added to scalar again. Result is stored in F8, and F8 is stored in the same memory location. Then again load minus 16, next element 998, store it in, take into the register F10. F10 will be added with F2, store in F12, then store the result in the same memory location. Again load minus 24, 8 byte, again we are reducing 8 byte, 997, then add, then store. Then we are checking, again we are doing minus 32, the next element, that means 996 will be compared with the initial element. I mean the element that is R2, that is 0. 99996 will be compared with 0. So in our previous example 1000 was compared with 0 for the first iteration. Here for the first iteration 996 will be compared with 0. So this total comparison will be reduced. Okay, so here in this example, within the same loop we are doing the same operations 4 times. Then we are checking the branching condition, branching operation, we are decrementing, then we are moving into the next iteration. this is actually called as loop unrolling. We are reducing this double add unsigned integer and branch operation 3 times in this particular case for each iteration. So totally these statements, so if one iteration this is reduced 3 times, 3 plus 3 6, for all other iteration also this will be reduced. Okay. So this is the explanation of the previous thing. So we are doing now. I am not going to explain all these things. How R2 will be set, that is 32. We have eliminated 3 branches and 3 decrements of R1 that we have already seen. Then without scheduling, now this is the stage. Simply doing loop unrolling. This is the stage. Just doing loop unrolling. Now it is not being scheduled. Now you can see that from the slide, you can see that this statement for a single loop, it will take total 27 clock cycles. For the load operation, there will be 1 clock cycle delay. So there will be 1 clock cycle delay here. There will be 1 clock cycle delay there. Okay, similarly, so I am not going to explain all those things. Similarly, for add operation there will be 2 delay. Then for D add unsigned integer there will be 1, and 14 insertion issue cycles. Normal insertion, there are total insertions available, and totally you can see that 6.75 clock cycles for each of the 4 elements. So by looking at the previous diagram once again, we can see that, so there will be some store. So totally 1 2 3 4 5 6 7 8 9 10 11 12 13 14. So 14 clock cycle for these instructions alone, and there will be some latencies or stalls in between, that is 13. So totally 27 clock cycle will be taken for the completion of this entire loop, for a single loop. So now for the single loop we are having 27 clock cycles required. Now that is to be done. So 27 into, now we need to repeat the loop how many times. So first time it is 4 instructions are mixed together. Now 1000 divided by 4. Okay, so that means we need to have the iteration only for that much time. Okay, so totally that will be multiplied with 27 to get the total number of clock cycles required will be always reduced than the previous one, because now we are having less number of loops only. So lot of clock cycles are being reduced because of the less usage of D-add unsigned integer and branch on not equal to in between. So we are actually reducing those stalls because of these instructions, and as the loop is being unrolled, we are reducing the number of branches also. So the total clock cycles required will also be reduced. So now for each iteration we require 27 clock cycle without scheduling, I am saying. Now if we implement scheduling, so in this so these two will be executed together. Either we will do loop unroll the loop, then apply scheduling. So now we are trying to schedule the same thing, just reorder the instruction. So just what the compiler is doing is, all the load will be moving upwards. So compiler will automatically move all the load into the top portion. So all the statements remains the same. Then it will do all the add operation. So there is no so all these are independent statements. All these are independent statements. Then it will do store. After to store, it will do double add unsigned integer. Then it will do to store operation. Then it will do branch on not equal to the condition. So just reordering or scheduling the already given set of instructions that is in a loop unrolled format. Now what is happening is, you can see that we are so the total execution time of the unrolled loop has dropped to a total of 14 clock cycles. So before it was 27 clock cycles. When it is being reordered, we can see that there won't be much delays in between. So 4 plus 4 8 plus 2 10 11 12 13 14. So if it is ordered in this way, there won't be any stalls in between these set of instructions. So this loop unrolling and adding scheduling into the unrolled loop will reduce the total number of clock cycles required for each iteration. So if one iteration takes only 14 clock cycles, so assume that if you are having initially it was 1000, now it is around 200 for example 200 iterations, 200 into 14, it will be always lesser than the previous. Initially it was 1000 into 9, that is 9000. Second, it was reduced to 7 into 1000, 7000. Now it is even reduced to less than 5000 itself. So the total number of cycles or lagging or latency between insertions will also be reduced, and effectively the overall number of clock cycles delay or the speed can be increased by using loop unrolling and by adding pipeline scheduling into the given set of instructions. So we have seen the examples by using a simple for loop, and the for loop is an iteration example where we require multiple number of branches or iterations. How we can reduce that? By using simple compiler technology, by using simple scheduling we can do that. And even for reducing that, we can do for larger loops we can do loop unrolling, and after unrolling the loop, again applying scheduling will actually reduce the total number of cycles required for completing the entire task, entire instructions present in a particular loop. Now we will just look at the summary of this loop unrolling and scheduling. Some points to be remembered. Determine that unrolling the loop would be useful by finding that the loop iterations were independent except for the loop maintenance code. So we are trying to find the loop iterations values where we are having independent statements. So in our previous example, all the statements are independent, but for the maintenance code, that is for checking condition and branching operation, we are having additional stalls to be generated. So second point is, when we are doing unrolling, we need to use different registers to avoid unnecessary problems. If we use the same registers, sometimes it will be correct, but there will be some confusion, collision in between. So it is always better to use different registers, as we have mentioned in our previous example. Eliminate the extra test and branch instructions. So that is what we are doing in our previous example. Try to reduce the number of branch instruction and the testing statement that is present in our entire loop. Then determine that the loads and stores in the unrolled loop can be interchanged by observing that the loads and stores from different iterations are independent. So we can do some interchange while doing scheduling. We can interchange load and store, depends on the set of instructions available. They can be interchanged by observing that loads and stores from different iterations are. If they are in different, we can do any interchange on that, so that we can reduce the number of clock cycles. So this is actually happens only based on the analyzation of the memory addresses and finding that they do not refer to the same. So even address reference should also should not be having any collision. Then finally we need to go for scheduling the code, preserving any dependencies needed to yield the same result as the original code. So finally it is just like an optimization in our compiler technology, that compiler initial code will be transformed into another format without changing the meaning. So that is actually for optimization. Similarly, for reducing the number of clock cycles, several processes are using this loop unrolling along with scheduling, and this technology or mechanism is usually referred to as the compiler techniques that are used for reducing the or increasing the performance of system, that is by improving instruction level parallelism. So here different instructions are executing with having latencies being reduced by using the compiler techniques like loop unrolling and scheduling mechanism. So that's it for now. We'll continue with same instruction level parallelism with some other technology details in our next session. Thank you.